now let's start with the fourth talk of today by Javier Morales from UT Austin. Javier is going to talk about existence, uniqueness, and the equilibrium for partially homogeneous stochastic Vizsche model.
Okay, thank you, Alessio. Well, before starting, I would like to thank all the organizers for giving me the opportunity to attend to this very nice conference and present this result. Okay. So first, I would like to. This is the equation that the model describes. Okay. So I would like to say a couple of words to motivate what is this equation doing. So this equation is for probability measures on the torus times the sphere. So you should think of the variables in the torus as position variables, and the variables in the spheres as velocity variables. So this is some kind of phase space where the only velocity allowed has to have modulus 1. Okay? So this is the equation. And if you write this equation, you can write this equation as a continuity equation on phase space. And when you do that, you can look at the associated Eulerian formulation, so like the ODE associated to the equation, sort of like what Ambrosio was doing in his lectures. And then you will see that this vector field associated to the continuity equation, when you look at the part that is tangent to the velocities, to the positions, so the tangent part of the vector field to the positions is the velocity on the sphere, so it has modulus 1. And the acceleration part is the sum of these two terms. So this logarithm is coming from the Laplacian, so you should think of it as being responsible for the diffusion. And this other part of the first term is a vector. It's a vector field of modulus 1. So this vector field is built as follows. For each x, you take the average of all the velocities in the sphere at that point x. So this is some sort of like local average momentum. And then you take the direction. Okay? So what these do is that each particle at point x will be changing its position by this velocity, and it will be accelerating by, they will be trying to accelerate in the direction of the mean trend of that point, but there is a diffusion that doesn't allow all the particles to get too concentrated. Okay. So we are going to focus on the homogeneous case, and we are going to see how the homogeneous case can be given the structure of a gradient flow. So before I do that, let me talk a little bit about what a gradient flow in Rn is. So suppose that you have a convex function E on Rn. Okay? So we are going to assume that this function is strictly convex, so it has a unique minimizer. Let me call it x min. If you look at the vector field given by negative the gradient of the function, then this is a vector field that has an attractor in the minimum of the function. Okay? So a solution to the gradient flow problem starting at a point x0 is just a curve that at each time has velocity negative the gradient, so it will go directly towards the minimum. Okay. So if you are solving the ODE associated to a convex function, to the gradient of a convex function, then there is a lot of very nice properties you can conclude. So first you see that if the Hessian of the function is uniformly bounded from below, you can take a parabola centered at the minimum, and you can bring that parabola from infinity until it touches the function from below, because the Hessian is bounded from below. So you trivially have that the function is bounded by a parabola of opening lambda, where lambda is the concavity constant. Okay? So that's the first inequality. And you basically can obtain all these inequalities by differentiating the function along the direction of the flow and using the elliptic condition. So you can derive all of this just by differentiating and using elementary calculus. Okay? So the hope is that once you have a parabolic equation or a dispersive equation and you know that it is the gradient flow of a function, then you can try to use these tools to study the dynamics, the long-term dynamics of the equation. So that's what we want to do in this talk. Okay, so this is the homogeneous equation, so we forget about the position variables. These are only the velocity variables. And then you see, well, if you want to look at equilibrium positions, you would like the force field to be 0. This is a sufficient condition for equilibrium. And for this, you get a bunch of equilibrium states. Because this condition, for each vector on the sphere, you can show that when you plug this in here, you get 0. So this is an equilibrium state. So you realize that there is no hope of finding a strictly convex functional for this equation, because basically you have a copy of SD minus 1 equilibrium states. Okay? Nonetheless, we still were able to get some results, so let me tell you a bit what we did. So this function is a gradient flow, well, it's a formal gradient flow in the space of probability measures. So Felix Otto, some years ago, he introduced the formal Riemannian structure in the space of probability measures under the basis time distance. And it's in this structure that this guy is going to be a gradient flow. So let me talk a bit about the formal Riemannian structure. Okay? So given a measure rho, you can talk about the tangent plane at the measure rho. It's going to be the set of functions such that this integral is finite. And now that you have identified the tangent plane, you want to define what the metric at that tangent plane is. Okay? So given two vectors in the tangent plane, you define their inner product like this. Okay? And then you need to talk about what is the relationship between, okay, if you have a continuous curve in your manifold, then you would like to say what the velocity of that curve at a point is. And in these heuristics, you say that a curve of measures has this velocity is for each time the curve is solving the continuity equation associated to this velocity field. Okay? So the Wasserstein distance, so this space under this distance is a complete metric space. Okay? It's the distance given by solving the optimal transport problem with quadratic cost. And Benamou and Brenier discovered that this distance can be expressed in this form. And this is exactly how you define the distance of a Riemannian manifold. No? The distance is just the minimum of the minimum of the square of the kinetic energy among all the curves that joins 2 points in time 1. Okay? So this is the Riemannian structure. This is all formal, but this guy is a metric space, a complete metric space over this distance. So all our estimates are going to be established using this distance. Okay? So now let me tell you how you see that this equation is a gradient flow. So according to our definition of curves, if you just look at the equation, you find that this equation has this velocity at each time, which is the same vector field that we saw before. And moreover, if you take this functional and you take the derivative of the functional along a curve with this velocity field, you find this, and you get that the derivative of the function along the curve is the inner product between this vector and the velocity. But when you take the derivative of any function in Rn, then when you use the chain rule, that's what you get. You get that the derivative with respect to time of E gamma is the inner product of grad E gamma dot. So this computation strongly suggests that the gradient of this functional should be this vector field and that the equation is solving a gradient flow. Okay? So now I have enough, I have all the language to state or part of what we produce, and basically we were able to show existence of the solutions to these equations. Let me remind you that omega is the renormalization of the momentum. So when the momentum is 0, this equation is not defined, it's very singular. So a key point for establishing existence is being able to control the momentum from below. So we were able to control the momentum from below. And we were also able to say that given any initial data with finite dissipation, then we can show that it converges to a fixed equilibrium state in the sphere. Okay? So let me remind you a bit of the functional. So these guys are trying to minimize. There is a competition between minimizing the entropy, but also trying to increase the momentum. Okay, so this is how this is different from the usual heat equation. Heat equation just tries to minimize entropy. In this guy, you have a competition between these two variables. Okay, so let me try to say a couple of words about the proof. Okay, so it's the key is the following. When you look at the functional and you try to evaluate whatever is Hessian mean? I mean, there have been a formalization of all these ideas by Ambrosio, Nicola Gigli, and Giuseppe Savare. These are all standardized ideas, and you can look at these theorems in books right now. And there is the notion of displacement convexity, and I don't have time to introduce all of that. So there is, in some sense, you can say that the Hessian of the functional is bounded from below by a negative constant. So this functional is not good enough to use the estimates I showed at the beginning, but the key is the following. The key is that at each measure, you can see the functional as the relative entropy with respect to the local equilibrium state. So at each measure rho, it follows that the functional applied at rho is equal to the relative entropy between rho and the equilibrium state that has the same average direction. Okay? Now, this functional, when you fix rho and only look at this as a function of rho with omega fixed, this functional is better. And also, it happens not only that these guys are equal at rho, but their gradients are equal at rho. Maybe one way in which this is to be expected is that this functional is like the minimum among all relative entropies when you let omega vary on the sphere. So they not only coincide at the point, they also coincide at first order. Okay? So once you obtain that the gradient of these two guys are the same, then you are in business because your problem is formulated in terms of the gradient. So this new functional is better. Its Hessian is bounded from below by 0. So if we compare all the estimates that we have in already at the beginning, we can try to use them under this language. And then we see that to use the estimate, you need strict positivity. Nonetheless, a sufficient condition to deduce these first inequalities is to have this inequality in here. This inequality can be deduced as a consequence of this one. This one, in this counterpart, is called the logarithmic Sobolev inequality. And the logarithmic Sobolev inequality, if you have it for a convex functional, then it is true. If you have that the relative entropy is strictly positive for a measure, then it is also strictly positive for bounded perturbations. And this is what this constant is. These constants come from a bounded perturbation of a log concave measure. Okay? So the point is that using an argument by Holly-Struck, we were able to still use the logarithmic Sobolev inequality, even though this functional was not strictly convex. And then we had all these inequalities at our disposal. And once you have them, it is pretty easy to get the estimates, because doing this computation in this language, you get dissipation of the energy. Okay? And once you have exponential dissipation of the energy, you can use that the distance is controlled by the relative entropy. This is called Talagrand's inequality, which is the counterpart of this inequality in the finite dimensional case. And that settles down convergence to equilibrium. Basically, once you have that the guy is converging to equilibrium, you can say that its momentum is also converging to the equilibrium one. So you can control this guy from below. And once you have a control in the momentum from below, you can use this estimate on the Hessian and this inequality to show uniqueness of solution. But there is an argument that has to be fixed, like using continuity of momentum. And well, this is it. So thank you.